Okay, so let's close our discussion of circular motion by talking about Newton's laws. As you remember, in the most general case of circular motion, you select the coordinate system carefully, you choose the origin at the center of the circular motion, and then you can write the position vector at some time t as r times r hat t. You can differentiate that once to find the velocity vector, and then differentiate again to find the most general case of acceleration. The acceleration vector is given as r times alpha theta hat minus r omega square r hat, and of course alpha was described as the angular acceleration and omega was the angular velocity. These are all at time t, of course. Now, what does Newton's second law tell us about force and acceleration, right? So obviously forces are related to acceleration via the equation F equal to ma, which tells us that in the most general case, for a particle moving in circular motion, and in circular motion that's, let's say, not necessarily uniform but speeding up or slowing down, there's a force acting on this particle. There has to be a force acting on this particle, right? And that force is given by F equal to ma. So we have m r alpha theta hat minus m r omega square r hat. Now, once we write the force vector like this, so what do we have? We have an unbalanced force F that's acting on this body. What we've done is we've selected clever choices of coordinates and resolved the force into those coordinates. Let's give them some names. We can call this the tangential force. The tangential force, you can say, that is the tangential component. It's the component of the force that's, in the direction of theta hat. And then you have another centripetal force. And the centripetal force is the component of F along r hat, right? Once you resolve it into components like these, it's immediately clear what their roles are. So of course you see that the centripetal component of the force, which is m r omega square, that's responsible for the centripetal acceleration, right? The centripetal acceleration being r omega square. So this is the component of the force that's responsible for keeping this particle on a circular track. Okay? The other component of the force, the tangential component, is what causes the tangential acceleration r alpha. As you remember, this r alpha component of acceleration describes how the particle's velocity is changing as it moves along the circle, right? So whether it's speeding up or slowing down as it's moving along the circular track. So this tangential force is responsible for producing this tangential acceleration. So that now it's kind of clear to us that if you have a centripetal force, you would have circular motion. Furthermore, if you have a tangential force, then this circular motion would not be uniform. You need a tangential force to speed up or slow down a particle on a circular track. At this point, it's helpful to think of the uniform circular motion case. So that special case where omega is equal to d theta by dt is a constant, such that then the angular acceleration, which is d square theta by dt square, is clearly zero. In that case, the force vector is then given by m r omega square r hat. In this case, of course, m r omega square, or the centripetal acceleration, the centripetal force, would be constant, the magnitude of F, right? If you plug in v equal to r omega, you can also write that down as mv square by r. So in the special case, you have this centripetal acceleration, r omega square, caused by this centripetal force, m r omega square. in order to cause a uniform circular motion, you need a inward pointing force which has constant magnitude but always points inwards, right? So this is something you probably are used to. Let's look at a problem in uniform circular motion to further understand the role of this centripetal force. So here's a problem that I picked from our Walker book, which is the reference that I recommended to you. So we have a stuntman driving a car over the top of some hill, this hill here, the cross section of which can be approximated by a circle of radius r equal to 100 meters. Now, what's the greatest speed at which he can drive without the car leaving the road at the top of the hill? So this illustrates a fine point that we want to make, that when studying circular motion, it's not as if you're confined to using these ideas in purely motion which is along a circle. Sometimes you have motion along a curve, but for small sections of the curve you can think of that as being basically circular motion, right? So what we have here is some car. Let's illustrate that by using just a point. It's moving up the ramp. So common experience tells us that if it's going really fast, then it goes up to here and then it just launches off, right? So we don't want that. Perhaps the stuntman is out of budget. He wants to play it safe. He wants to find the maximum velocity such that his trajectory or his car just presses along the hill, does not fly up like that. How can you find this? Well, what has to happen is that his car along these points has to travel in an arc of a circle of radius 100 meters. Well, how can he do that? He can do that if there's a centripetal force on him that is given by mv square by r. The maximum value of v square that is given by the maximum possible value of centripetal force can determine for us the greatest speed at which he can drive without the car leaving the road at the top of the hill. It's important to understand something, so let's note that. It's important to understand, so it's very important and often a misconception that people deal with. It's important that centripetal force is not a special type of force. So centripetal force what centripetal force is that it's just a component of the net force. It's just a component of the net force on a body that is radially inwards. If you have multiple forces on a body, of course you find the total force on the body by adding up those forces vectorially. Then if you have a component that always points radially inwards, no matter where the particle is, it points towards some point, then what will happen is that this force is going to cause that body to move in a circle, right? That's what the centripetal force is. So since the centripetal force is not a special type of force, you want to, in a situation where a particle is moving in a circle, you want to look at the forces acting on the body and you want to identify which forces are acting towards the center. In this case that we discussed a minute ago, there's actually only two forces acting on this thing. Since the car is moving at constant speed along the ramp, there's no, along the hill, there's no component of force along the hill. What the component of forces are mg and n, right? Whatever those are. So how can it complete this circle? By going at some velocity v such that the only force that acts radially inwards, let's say at this point, which is mg, this mg has to support this body going at velocity v along this circular trajectory here, right? So if we write that down in equations, we get F equal to mv square by r equal to mg. So it's not like mv square by r is some kind of special force that's acting on the particle while it's here. We are just saying that this mg, which at this point points radially inwards towards this circular motion, right? This force must provide the required centripetal force such that the body is able to move at velocity v along this circular path, right? If you put in any more velocity, if you try to drive any faster along this, then what will happen is that this quantity will be too large for mg to make it up, in which case you would have not sufficient centripetal force to complete the circular track of radius 100 meters, so that what the car will do is gonna fly off, right? If you now rearrange this, you get v equal to r mg root over, and that is the solution of this problem. This is the maximum speed at which the stuntsman can drive this car, and the only force that's acting radially inwards, which is mg, will be able to provide the centripetal force needed in order to carry out this arc of a circle motion. So you have to understand that these ideas of circular motion don't necessarily have to apply to motion that completes a whole circle or something. Many a times particles go through a curved trajectory, and in small sections of the curve it looks almost circular, and the behavior of the particle for that small portion, like here you went through an arc of a circle, so the behavior of this particle is as if it's undergoing circular motion. So it's very helpful to understand these formulae and apply them. Alright then, in the quiz you want to plug in the numbers, and right, I missed something in the formula. Of course you can cut off m from both sides, right? So yeah, that's why the problem does not supply you a mass of the car. That's a general tip. If you ever see a problem where mass is not supplied to you, it might become clear to you that perhaps it's not needed. Alright, in the problem we just ask you to plug in some numbers into this formula and see for yourself what the maximum velocity with which you can drive along this hill is. Okay, thank you. Lecture 8 over.